Okay, thank you. My name is Shlomi Reuveni. I'm from Tel Aviv University, and today I would like to tell you about a recent discovery that we've made regarding the universal linear response of the mean first passage time. So this talk is going to be about first passage processes and how they respond to perturbations, and I would like to advertise a result basically stating that this response is in many ways universal. Before I start, I want to give credit to a very talented PhD student, Tomer David Kedar, who led this research. The paper, Universal Linear Response of the Mean First Passage Time, is already on the archive, and you're welcome to check it out. Okay, so let me start with perturbed first passage processes. What are they? They are the basis for our discussion. So of course, we all know about first passage processes. The classical example is a particle diffusing until it finds some target. And you can imagine that this process has been going on for a while, but then at some point you turn on a field, and from this point onward, the time evolution is going to be completely different. And this will, of course, affect the first passage properties of your particle to the target. It will change the mean first passage time and its distribution. So you took a first passage time process and you perturbed it by the introduction of a field. You can think about another example. Maybe you own an asset and you're following the price of this asset, and perhaps you decided ahead of time that you're going to sell it when it reaches a designated target price. But then what could happen? Some externality, a black swan, as they call it in finance, will come in and rattle the markets. Maybe an earthquake, maybe some climate catastrophe, I don't know what. And what was before is no longer after. The dynamics is completely changed, and this will, of course, again affect the first passage properties, the first passage time, and the dynamics of the process. So again, a first passage process reaching a target price that was perturbed by an externality. Another example, which is very popular nowadays, maybe you're training a neural network to tell the difference between dogs and cats. And you're following the accuracy in the prediction of this neural network as a function of time, the time that you're training it. But because you're training using stochastic gradient descent, the time to get to a target accuracy is random. This is now your first passage time. And training a neural network is, in fact, the first passage process. And what people noticed, including us, is that you can perturb the network in various different ways. And if you do it cleverly enough, you can shorten the time it takes the network to get to the training to get to the target accuracy, saving time and also money because training these networks en masse costs a lot of money. So this is another example of a perturbed first passage process, but you can construct infinitely more. Any process with a start and a finish and some time between them is a first passage process. And now you can come with your favorite perturbation and poke it. You'll have a perturbed first passage process. What I want to ask today is, what is the response of first passage processes to perturbations? And of course, the motivation comes from things that we know in statistical physics, in particular linear response. So in equilibrium, you have some observable, and it has a certain value, but then you can come and perturb the system with some small amplitude, and your observable will respond to this perturbation in a way that is linear, proportional to the amplitude times some response function. So we want to do something similar for first passage processes, but the problems are many. One of them is that we're really out of equilibrium. We're not even at a steady state. First passage processes are inherently transient. So they have some dynamics, they reach the target, and then they end. So we're really out of the game for these types of frameworks. We need something different. So these theories were usually framed in the context of equilibrium or then extensions to non-equilibrium steady states. But what do we do here? It's not clear for transient processes. Another problem that we have is that we want to be relevant to perturbations that we see around us. A black swan is not a small perturbation, it's a huge perturbation to the markets. When people train neural networks, they do very large perturbations to the training process. And so if we want some kind of linear response theory that is relevant to the perturbations that we see, the small parameter in it cannot be the amplitude of the perturbation. It needs to be something else. What is it? It's not clear. Another problem that we have is the response function. How do we even compute the response function in the absence of standard tools like fluctuation dissipation that we don't have in general for first passage processes? So what do? We want a linear response theory for first passage processes, but it's not clear where to start. A clue came from a recent development in non-equilibrium statistical physics. This is stochastic resetting. There is one perturbation in particular, stochastic resetting, for which we already have a linear response theory. So what is stochastic resetting? Here you see a first passage process. There's a particle diffusing in an energy landscape. It starts somewhere and it wants to go up to the top basin. And you see there's some sort of a reset event which takes the process back to its initial position. So this is resetting, and why is it stochastic? Because usually you think about it, you think that you reset with some rate lambda, meaning that at every infinitesimal time interval delta t, you have a probability delta t times lambda to reset. And if this lambda is small, then we know, this is something that we proved, that the mean first passage time under resetting is the mean first passage time without resetting, in the absence of the perturbation, plus lambda, with the resetting rate, times our response function. And what is interesting is that this response function is completely universal. It does not depend on the details of the underlying process at all, only through the mean first passage time in the absence of the perturbation and the variance in the first passage time in the absence of the perturbation. So this is akin to what we know from statistical mechanics. Fluctuations here in the unperturbed first passage time, they come to predict or determine the linear response to the perturbation, which is here stochastic resetting. And moreover, they set the sign of this linear response function. Whenever the standard deviation of the first passage time process is larger than the mean, the unperturbed first passage time process, this sign is negative, and you're assured that the introduction of stochastic resetting will lower the mean first passage time of your process. And this had many applications to expedite first passage processes. I'll just briefly mention two. In search processes, should you just search for the target continuously or search and then return, search and then return? Well, all you need to do is look at the standard deviation of the original first passage time, unperturbed, and compare it to the mean. If the standard deviation is larger than the mean, you should reset. This will, for sure, lower the mean first passage time. If you're doing computer simulations and you're interested in certain molecular transitions, say you're looking at a folding of a protein and its transition from unfolded, misfolded, and folded states, should you reset this process on the computer to see more transitions from the type that you're interested in? Well, just look at the standard deviation of the transition that you are interested in. This is a first passage process. Compare it to the mean. If the standard deviation is larger, you should reset. This will enhance sampling greatly. And this is also something that we've shown and written about. Okay. Now, how do we go beyond stochastic resetting? The linear response that I showed you, it's good for stochastic resetting, an arbitrary first passage time process, but we're limited to a very specific perturbation. We want to marry arbitrary perturbations with arbitrary first passage time processes. How do we do that? And this is where Tomer came in with his insight, and what he said was the following. Well, stochastic resetting is not a small perturbation. Sometimes I bring the particle from very far away. What is small over there in the linear response theory is the resetting rate. So why not think about an arbitrary perturbation applied with a small rate? So this was the key insight, and from there, we were able to continue. And in this example, you see a particle diffusing, and then I come and I kick it, and I can think about a situation where I do this with a constant rate lambda. Okay, of course, now consider arbitrary perturbations and arbitrary first passage times, and what we find is the following thing. The mean first passage time of the perturbed process is, again, the mean first passage time of the unperturbed process plus lambda, the perturbation rate, times a linear response function. And what's interesting is that, again, this linear response function is completely universal. It only depends on the mean and variance of the unperturbed first passage process. And then there's a little price to pay, going from stochastic resetting to an arbitrary perturbation. You also need to know another first moment. This is the mean time for completion from the moment the perturbation was introduced. Okay? Otherwise, it's all general. And I want you to note here that fluctuations matter. It's not enough to know this mean and this mean. The variance in the original first passage process matters. It matters to the magnitude of the response, also to the sign of the response. So mean level analysis will not work here. Fluctuations must be taken into account. So we have a linear response theory for first passage processes, but what is it good for? What can we do with it? One thing that we can do with it is prediction, okay? So we can predict the response of all sorts of different perturbations on all sorts of first passage processes. Here's one example. You take an overdamped Brownian particle in a linear potential, and with a rate lambda that is small, you let it go, and with a small rate lambda, you introduce a different potential, say a logarithmic potential. What will this do to the mean first passage time of this particle to a target that is L away? So to solve this problem, even to just tell me if it will increase or decrease the mean first passage time, you would need to write the differential equations that describe this process, solve them, work hard. Now we're saying that this is not required. All you need is the mean and the variance of the first passage time without the perturbation. So this is just mean and first passage time of a particle diffusing in a linear potential, textbook problem. And then the mean first passage time from the moment the perturbation has been introduced. This is also rather easy to compute. All you need is the distribution of positions where the particle is when the perturbation is introduced. And from this moment onward, you're on a logarithmic potential. You have the mean first passage time again to the target from textbooks. So this is very easy. And when you do that, you discover a very non-trivial phase space which divides space. Here we have the strength of the log potential measured in units of kBt. Here we have the Peclet number, which is quantifying the strength of the linear potential, the interplay between diffusion and drift. And you see that there are areas where first passage is hindered by the introduction of a logarithmic potential, and then areas of the phase space where the introduction of a log potential expedites first passage. So this is very nice, but of course we had to analytically, or we had an ability here to analytically compute these parameters that are required. What happens when you don't have that? When you have something that you don't know how to compute mean first passage times for and standard deviations and this time tau bar? Well, then you can just measure them and plug them in the equation and do predictions. And this is exactly what we did when we applied a version of this theory for improved training of neural networks. This is a joint collaboration. It was a collaboration with Barak Hirschberg and Sagi Meir, also from Tel Aviv University. And here, people are applying all sorts of perturbations to the training of neural networks, but they don't know what will speed up training and what will hinder training. How can you know before trying? So now there is a way. You just need a little bit of sampling. You need to know how the process behaved, the mean and the standard deviation of it in the absence of a perturbation. And then you need to perturb it at a low rate, measure the time to completion from the moment the perturbation has been applied. And if you did that, you can predict for much higher rates of perturbations. And then you can choose which is the perturbation that you want to apply ahead of time before trying. You will know that it's better than the others. So this is a very nice tool that we now have. I'll just finish with another type of thing that we can do with this, and this is inference. Of course, we can also use this in reverse. Perturb, and then from the perturbation, infer the fluctuations. And with this, we actually came up with a way to infer single molecule fluctuations from bulk measurements. Suppose you're interested, this is my last slide, suppose you're interested in the time it takes some molecule to be degraded. You only know the mean. This controls the concentration in the system, but you don't know the fluctuations. What you can do is you can come with a different molecule, perturb the degradation of the regular degradation process, measure the response of the concentration to this perturbation, and from this we show that you can infer the standard deviation of the lifetime and also the entire distribution. So in this case, we went beyond linear response and predicted the entire distribution of the degradation time from the response to the perturbation. Again, the first example that at least we know of extracting single molecule fluctuations from bulk measurements, just measurements of concentration. With this, I would like to end. Thank you very much. Thank the linear response team, which is a one-man's team, Tomer David Kedar, members of my group and funding. Thank you very much.